So today we're in section 9.2, and 9.2 is about linear regression. If you recall, in section 9.1, we were always trying to see if there was any correlation between several data points. We would be given 8 or 10 or 12 data points. We wanted to know, was there a positive correlation? Was there a negative correlation? Or was there no correlation? If we found a correlation, we wanted to see if that correlation was a significant correlation. Did it actually mean something? So now we want to know, if we find a significant correlation, what do we do with it? What are our next steps after we've determined that a correlation is significant? That brings us to the regression line. What the regression line is, sometimes it's called the line of best fit. It's the linear equation that best models the given data. It helps us make predictions about y for given values of x. And there are specific processes for finding this line. Now you'll notice that we're leaving a blank on this definition because we're going to discuss a little bit before we fill in that next part. Otherwise the next part doesn't quite make sense. So let's assume we have the following scatter plot that clearly has a strong positive correlation. You can see that these dots are arranged in a manner such that they're going upward from left to right, and that they feel like there's a straight line action there. Not perfectly straight, but kind of a fuzzy straight line moving from bottom left to the top right. If we graphed a regression line, it might look like this. So you can see a line that's kind of traveling through the midst of those points, and it's following that general path. The points aren't falling on the line, but they're surrounding the line. So you can kind of get an idea that this is like an average motion that the lines are taking. When we draw this line, there's always going to be some vertical distance between some of the points and the line. And those vertical distances are called residuals. So if I was to graph those little vertical lines here, you can see that some of the points are above the line, some are below the line, and that these little distances are called residuals. So we'll flash them there for you so that you can see them. Now let's give them names. Each one of those distances is going to be called some kind of a d. Now we don't want to just call them all the d because the distances aren't all the same. So we'll number them as well. So we'll have d1 and d2 and d3, d4, d5, d6, d7, d8, d9, d10, d11, d12, d13, and d14. So we have 14 different distances on this particular graph. And those residuals are what hold the key to finding the regression line. So now we're ready to go back and finish off our definition for the regression line. We said it was sometimes called the line of best fit, and that the regression line is the linear equation that best models the given data. What's missing? Well, what's missing is that it's the line for which the sum of the squares of the residuals is a minimum. So the residuals are a lot like deviations when we discussed the standard deviation in chapter 2.4. Remember, when we did deviations, we followed a formula, and some of the deviations turned out to be negative and some turned out to be positive, and that caused a problem for us because distance shouldn't be negative. The same kind of thing happens here when we're computing a residual, where points that are below the line give you a negative residual and points that are above the line give you a positive residual. So when we were doing the standard deviation, to get rid of the negativity problem, we squared the deviations. That way all the negatives went away. We're going to do that same thing here with the residuals. If we square the residuals, then all those negatives go away. So that's why we say it's the line for which the sum of the squares of the residuals is a minimum. So if you think back to the scatter plot that we saw before, we sketched in a regression line, but How do we know it wasn't this line? So we've drawn another line in the midst of those points that looks like it might be the regression line. Or maybe a third line. What about this one? So all of those are candidates. So how do we actually find the regression line? So we have a process. To find the regression line, you're going to take each residual and square it. You add them together, and you want this sum to be as small as possible. The line with the minimum sum is the regression line. Now, in practice, that's not the way we're going to do it. The reason for that is technically there's infinitely many possible regression lines that would be traveling through the midst of these points. And to be able to do that calculation infinitely many times is not possible. However, we have some friends in mathematics. There are our buddies in calculus. And in calculus, one of the problems that they do a lot is minimization and maximization. So we're basically setting up a sum here, and we want the minimum sum. Calculus has the ability to do that. Well, this is not a calculus-based statistics course, so how does that help us? Turns out that they've come up with formulas that give us the values we need to determine the regression line. So yay to the people in calculus, they've helped us out. We'll take from them what we need and be able to go through this process now. So, the regression line. The equation is going to be given by y with a little circumflex on the top. We'll call that y hat equals mx plus b, where y hat is the predicted y value for a given x value. So we call that value y hat. The reason we don't call it y is because y is going to be the second coordinate in each ordered pair. That's not necessarily the same as the value that comes out of this equation. Let's go back and look at the graph we had that showed the residuals. On this graph, you can see that we have all 14 points, and the regression line runs through the middle of those. The y values are going to be the y coordinates of the actual points. What the y hat value is it's the value of the y coordinate of the line for the same x value as the point. So you'll notice if you look at, for instance, D3 here. D3 on the graph is above the line. So it has an x coordinate and a y coordinate. What the y hat value is it's the y coordinate of the point on the line right where that residual distance meets the line. They clearly have the same x coordinate because they're the same distance over from the axis, but they have different y coordinates. So the y coordinate is the value of the point. The y hat coordinate is the value of the point on the regression line. So that's why we don't call them both y. We call one y and one y hat. Y hat is the predicted value. So now our question is, how do we find m and b? Well, we have formulas. The formula for the slope m, it looks very complicated. But when you think back to all the symbols that we've learned and what they mean, this is fairly simple to compute. So m is equal to n, which is the number of data points, times sigma of x times y, minus the quantity sigma of x times the quantity sigma of y, over n times sigma of x squared, minus the quantity sigma of x squared. So what do those symbols mean? Well, again, n is the number of data points. Sigma, whenever you see that symbol, means add them up. So it means we're doing a sum. So we are going to take each x and multiply it times its y, and then add those all up. we're going to take the sum of all the x coordinates and the sum of all the y coordinates, multiply those together. And if we subtract those two values, we get our numerator. Then we'll take each x value and square it and add them all up and multiply them times n to give us a value in the denominator, and then subtract the sum of the x's squared. So basically we're doing a whole bunch of additions and a few multiplications, and that gives us our m. And we're just using the x's and y's from our ordered pairs that we have in our data points. To find the value of b, which is our y-intercept, b is y bar minus m times x bar, which is sigma y over n minus m times sigma x over n. So what is sigma y over n? Well, that means you add up all the y's and divide by how many data points there were. That's the average of the y coordinates. And sigma x over n, you add up all the x's and divide by the number of data points. That's the average of the x coordinates. That's why they're called x bar and y bar. We saw that when we were talking about averages, that a sample average would be x bar. Well, so this is the average of the x coordinates and the average of the y coordinates. And once you have m and b, you have enough to write the equation of your line. So let's take a look at the features of this regression line. X bar is the mean of the x values. Y bar is the mean of the y values. N is the number of data pairs. And we know that this point, x bar comma y bar, will always be on the regression line. So we know for sure one point that falls on the line. X bar comma y bar always falls on the regression line. Okay, so let's take a look at an example. The following data represents the number of yard workers, x, and the average number of minutes needed to complete a yard, y. There is a significant correlation at the alpha equals 0.01 level of significance. Find the regression line for these points. So we have our data. The x's represent how many workers we have, and the y's represent how long it takes to complete the yard. So if we had 3 workers, the yard takes 22 minutes to complete. If there were 8 workers, it takes 10 minutes, 7 workers, 14 minutes. If there are 4 workers, it takes 22 minutes. If there are 3 workers, it takes 27 minutes. If there are 5 workers, it takes 19 minutes. If there are 4 workers, it takes 23 minutes. 7 workers, 13 minutes. 3 workers, 24. 6 workers, 16. You might notice that for the same value of x, for instance, the x equals 3, we have different y values. Why would that be? Well, it's because these are actual data times. We actually had 3 workers working on a yard, and on one day it took them 22 minutes. On a different day it took them 27, and on a third day it took them 24 minutes. So this is real world data that doesn't always come out the same way. Maybe they were working harder one day. Maybe there were issues in the yard that required a little extra time. This is real world data. This is not perfect world data. So the same x will not necessarily give you the same y value. Moving on, let's look at our solution. So we're going to try to apply these formulas. M equals n times sigma xy minus sigma of x times sigma of y all over n times sigma of x squared minus sigma of x quantity squared. And the b is equal to y bar minus m times x bar, which equals sigma of y divided by n minus m times sigma of x divided by n. So we're going to take our table and expand it. We're going to take a lot of work to do this problem here, so we need to expand that table. We need to find values for x squared, which don't currently appear in the table, and for x times y, which also does not currently appear in the table. So we've added 2 extra rows to our table. So we have the row for x's, the 3, 8, 7, 4, 3, 5, 4, 7, 3, 6. the row for y's, which is 22, 10, 14, 22, 27, 19, 23, 13, 24, and 16. We've added a row underneath for x times y and a row for x squared. And we've put a column at the end for the sum because we're going to need to know the sum for each one of those rows. We'll start with the x times y row. So when the x is 3 and the y is 22, the x times y is 66. When x is 8 and y is 10, x times y is 80. When x is 7 and y is 14, x times y is 98. When x is 4 and y is 22, x times y is 88. When x is 3 and y is 27, x times y is 81. When x is 5 and y is 19, x times y is 95. When x is 4 and y is 23, x times y is 92. When x is 7 and y is 13, x times y is 91. When x is 3 and y is 24, x times y is 72. And when x is 6 and y is 16, x times y is 96. Then we'll compute all of our x squareds. So the first x is 3, 3 squared is 9. Then we have 8, 8 squared is 64. 7 is our next x, square that and we get 49. When we square the x equal to 4, we get 16. When x is 3, the square is 9. When x is 5, the square is 25. When x is 4, the square is 16. When x is 7, the square is 49. When x is 3, the square is 9. And when x is 6, the square is 36. So now that we've computed x times y and x squared, we're ready to find the sum for all 4 rows. We'll start with the sum of the x's. 3 plus 8 plus 7 plus 4 plus 3 plus 5 plus 4 plus 7 plus 3 plus 6 is equal to 50. For the y's, we add those up. 22 plus 10 plus 14 plus 22 plus 27 plus 19 plus 23 plus 13 plus 24 plus 16 is 190. With the x times y's, 66 plus 80 plus 98 plus 88 plus 81 plus 95 plus 92 plus 91 plus 72 plus 96 is 859. And for the x squareds, 9 plus 64 plus 49 plus 16 plus 9 plus 25 plus 16 plus 49 plus 9 plus 36 is equal to 282. So we have our 4 sums which are required in the formulas for M and B. So let's go ahead and put the information we need in a place that we can see it. The final info from the table looks like this. We now know that the sum of the x's, sigma of x, is 50. The sum of the y's, sigma y, is 190. Sigma xy is 859. And sigma of x squared is 282. Because when we found those sums, remember sigma means sum, so sigma x means the sum of the x's, which was the value for the first row, 50. Now we have all 4 values we need, so let's go ahead and look at our formulas. We'll start with the formula for M. M equals n times sigma xy minus the quantity sigma of x times the quantity sigma of y over n times the sigma of x squared minus the quantity sigma of x squared. So we're going to insert the values in the correct positions. Remember that n is 10 because we had 10 data points. So this is 10 times 859 minus 50 times 190 in the numerator. And in the denominator, it's 10 times 282 minus 50 squared. So now we do these multiplications. 10 times 859 is 8590. And 50 times 190 is 9,500. 10 times 282 is 2820. And 50 squared is 2,500. We have 2 subtractions to do. 8590 minus 9,500 and 2820 minus 2,500. So in the numerator, we have negative 910, and in the denominator, we have 320. We'll reduce this fraction to negative 91/32. Again, fractions give us a nice complete value, whereas decimal approximations will either lose some value or gain some value, so the fraction is usually the better answer. Let's go ahead and find the value of b. So we'll get rid of this stuff and just keep what we need, that m is equal to negative 91/32. To find b, we use the formula y bar minus m times x bar, which is the sigma y over n minus m times sigma of x over n. Sigma y is 190, n is 10, so we get 190/10, minus m, which we just computed as negative 91/32, times sigma of x, which is 50 over n. Now, the first and last fraction, the 190/10 and the 50/10, both reduce. So 19/1 plus, when we go ahead and multiply, the negative sign on the 91/32 and the minus sign combine to give us a plus sign. And 91 times 5 is 455. The reason that it's 5 is 50 divided by 10 is 5. And then we have 32 in the denominator. To add two fractions, we need a common denominator, which is going to be 32. So we multiply 19 by 32, and we get 608/32 plus 455/32. And when we add those together, we get 1063/32. That's our value of b. So now we have everything we need to finish this problem. We have the value of m is negative 91/32, and the value of b is 1063/32. So the equation for the regression line is y hat equals m times x plus b. So we insert the negative 91/32 for the m and the 1063/32 for the b, and our regression line is negative 91/32x minus 1063/32. If we wanted it in decimal form, it would be negative 2.84375x plus 33.21875. So those would be your regression lines in fraction form and in decimal form. So thinking back to section 9.1, there was a problem that we encountered. It was a practice problem. The following data represents the number of students in 8 fifth grade classes, X, and the average number of discipline problems per week, Y. Find the correlation coefficient for the data and determine if there is a significant correlation at the alpha equals 0.01 level of significance. And our data was this. When there were 24 children in the classroom, there were 3 discipline problems that week. With a classroom of 29 students, there were 7 discipline problems per week. When there were 26 students in the classroom, 4 discipline problems. 23 students, there was 1. 30 students, there were 6. With 25 students, there were 4 problems. With 26 students, there were 5 problems. And with 25 students, there were 5 problems. So what we want to do is find the regression line for these points. So again, we're going to look at these formulas. M equals n times sigma of xy minus sigma of x times sigma y over n times sigma x squared minus the quantity sigma of x squared. And b equals y bar minus m times x bar, which is sigma of y over n minus m times sigma of x over n. We're going to need to expand the tables again because we need to have the values for x squared and for x times y. So we'll take the data table that we originally had with our 8 values of x, 24, 29, 26, 23, 30, 25, 26, and 25, and our 8 values for y, 3, 7, 4, 1, 6, 4, 5, 5. And now we'll write a row for x times y and a row for x squared, and then add on a column at the end for the sums of those data values. So we'll start with x times y. 24 times 3 is 72. 29 times 7 is 203. 26 times 4 is 104. 23 times 1 is 23. 30 times 6 is 180. 25 times 4 is 100. 26 times 5 is 130. 25 times 5 is 125. For the x squareds, 24 squared is 576. So when x is 29, we square it and we get 841. 26 squared is 676. 23 squared is 529. 30 squared is 900. 25 squared is 625. 26 squared is 676. And 25 squared is 625. Then we'll add up each row. For the x's, the sum of 24, 29, 26, 23, 30, 25, 26, and 25 is 208. For the y row, 3 plus 7 plus 4 plus 1 plus 6 plus 4 plus 5 plus 5 is 35. For the xy row, 72 plus 203 plus 104 plus 23 plus 180 plus 100 plus 130 plus 125 is 937. And for the x squared row, 576 plus 841 plus 676 plus 529 plus 900 plus 625 plus 676 plus 625 is 5,448. So we'll keep the values that we need. Sigma of x is 208. When we added up the x's, we got 208. Sigma of y is 35. Sigma of x times y is 937. And sigma of x squared is 5448. We're going to go ahead and compute m first. M equals n times sigma xy minus the quantity sigma of x times the quantity sigma of y over n times the sigma of x squared minus the quantity sigma of x squared. So now we're going to go ahead and insert these values. Remember that n is 8 because we had 8 data points. So n times the sum of xy is 8 times 937. Sum of x times the sum of y is 208 times 35. N times the sum of the x squareds is 8 times 5448. And the sum of the x's squared is 208 squared. So we're going to go ahead and do these 4 multiplication problems. 8 times 937 is 7496. 208 times 35 is 7280. 8 times 5448 is 43584. And 208 squared is 43,264. Now we have 2 subtractions to do, one in the numerator, one in the denominator. In the numerator, 7496 minus 7280 is 216, and in the denominator, 43,584 minus 43,264 is 320. We can go ahead and reduce this fraction quite a bit, all the way down to 27 over 40. So that's our slope, m. We'll go ahead and clear this out and just keep what we need. We need the m is 2740. Now we can go ahead and calculate our value for b. b is going to equal y bar minus m times x bar, which is sigma y over n minus m times sigma x over n. So sigma y is 35 over 8 minus 27 over 40 times sigma x, which is 208, over n, which is 8. We'll go ahead and simplify here. So when we multiply those 2 fractions after the minus sign, we end up in reduced form getting 351 over 20. And we need a common denominator here. The common denominator is going to be 40. So we'll multiply the first fraction top and bottom by 5, and the second fraction top and bottom by 2, which gives me 175 over 40 and 702 over 40. We go ahead and subtract, and we find that our b value is negative 527 over 40. That doesn't reduce. So now we'll go ahead and take away all that work and just keep what we need. We have the m is 27 over 40, and the b is negative 527 over 40. So now we're ready to write the equation of our regression line y hat. So y hat equals mx plus b, which is going to be 27/40 x minus 527 over 40. That's the equation of our regression line. In decimal form, it would be 0.675x minus 13.175. 27 over 40 and 527 over 40 are nice decimals, so it looks pretty good in decimal form as well. So this is our regression line for these 8 points. It's a long process when you look at it. No part of it is particularly difficult. We're just basically taking numbers in a table, multiplying them together, squaring them, and adding them up, and then putting them into spots in a formula that requires some multiplication, subtraction, and division. We're not doing any super complicated mathematical processes. We're just relying on the 4 basic arithmetic principles that we learned in elementary school. But it's just applying them in this particular way. So we've got a bunch of happy faces popping up on the screen. Somebody must be happy. It's probably me. I'm usually a pretty happy guy. So why am I so happy? It's because the TI-8384 calculator can help me find the equation of this regression line. Right, so it has a process by which it can take all of that work that we did building the table and do it in the calculator for us to come up with our answers. So how do we do that? Well, our first step is to press the Stat button. And when you press the Stat button, what you'll see is this particular screen. It's the Stat Edit screen. And the Edit tab at the top is highlighted, and the first choice on the list is also highlighted. If we go ahead and press Enter, then we're taken to the Stat List screen with L1 and L2 and L3 across the top. Those are the lists that are built into our calculator. If your lists are not empty, then what you can do is use your arrow keys to go up and highlight the name of the list and press the Clear button. And then when you come back down into the list will be empty. So if you already have data in your list, for instance, if you borrowed a calculator from the library and there's already data in the lists, you can clear out that data quickly by highlighting the name of the list, pressing Clear, and coming back down into the list. What we're going to do on this list screen is we're going to enter the X coordinates as L1 and the Y coordinates in L2. It's important that you keep them in the same order. Remember, part of this process is multiplying X times Y. So if you change the order, you'll be multiplying different X's and different Y's together, which will mess up the calculation. So make sure you maintain the same order. So we'll enter all of our values. And then once we have that all entered, we go ahead and press second and the mode button, which returns you to the home screen. And if you press the Stat button again, you go back to our Stat Edit screen. This time we're going to use the arrow key to move over to the Calc tab at the top. So when we get to that screen, we want to scroll down to the 4th entry, which is Line Reg AX plus B. That means linear regression to give you an equation in the form AX plus B. That's the one we want to do. If we press Enter on that screen, then it puts Line Reg AX plus B at the top of your home screen. Pressing Enter again, you'll see this. It comes up with all this information. Y equals AX plus B, A equals 0.675, B equals negative 13.175. It gives you R squared, which we don't need at this point, And R, again, is the correlation coefficient that we saw in section 9.1. So this is a strong positive correlation, right? We have a 0.87 correlation. And this is our regression line. See, the A is our M value, 0.675, and the B is our value for B from the equation, which is negative 13.175. So A is your M, and B is the B. So that brings us to an end of this particular section. Make sure you look for your homework on Pearson. Have a great day.